Force diagram's done. In which direction is the acceleration? I've seen a couple people pointing that way. I assume, Keelan, you were trying to go in that direction, all right? Yep, Martina's got it too.
Right as I have positives.
Pardon?
Right as I have positive.
You said right to positive?
Yes, sir.
No. Not that way. You're jumping to the next step, right? Coordinate axes? This is why I don't go with X and Y. Acceleration's done. One of the axes be in the direction of acceleration, which is that way. That's why I have more than just I wanted a valve there. It actually is done in that direction. So my coordinate system, I'm going to set up one axis to go down the ramp, that's I hat, and one perpendicular to it. And it really doesn't matter if J's pointing away from the ramp or towards the ramp, but I hat being down the ramp makes life a little bit simpler. Decomposition. I have two forces there acting on the box. I care about the acceleration of the box. This right here is the part that I care about right there. Check that off for posterity. Are either of these forces not in the direction of, or not parallel or anti-parallel to one of my axes?
No. Or yes.
Yeah. Normal force is in the same direction as my J hat. Weight is not parallel to the ramp or perpendicular to the ramp, not parallel to acceleration or perpendicular to acceleration. We need to break weight up. We need to figure out how much of that weight is down the ramp, how much of that weight is into the ramp. I'm going to go through the geometry of it to talk about how we break it up, geometry/trig. At some point, we will just skip that step, even though some people will still ask, and that's fine. But I'm trying to figure out the direction of weight, and I know weight acts straight down. So I'm just drawing the arrow at convenient length right there. That angle there is theta, that's the angle down here. This is, what I'm trying to break up is my hypotenuse. And I'm going to make a right triangle. My right triangle, the two sides of the two smaller sides of the right triangle are both parallel to my coordinate system. Parallel or anti-parallel. So I've got part of it going this way, and I'll go too far, part of it that way. That's the triangle I'm breaking up. Blue lines are the components. Those are perpendicular components. And I know this angle down here, or this angle up here, is equal to theta. Now the way I've drawn it, since I make on pretty much all the angles when I draw on the board 45 degrees, even though it's not officially, but this is the way I draw them, you can't easily tell which one is going to be theta. If I drew it a little bit better, you might be able to tell just by visual inspection. But let's assume we don't have visual inspection to do this, and then we'll do a visual inspection version. If this is a right angle here, what is the angle here?
Also right angle.
So if that's a right angle and that is theta, what is this angle here?
90 minus theta.
Yes, otherwise known as the complement. Now I'm going to signify the complement of theta as theta prime. So theta plus theta prime is equal to 90 degrees. They're complements of each other. What is the angle between my weight vector and the ground?
So,
Pardon?
V0 is 57 degrees zero.
I'm talking about the angle between that and this.
90.
Yep, that's a 90-degree angle also. Therefore, this angle right here is also 90 degrees. Therefore, what is this angle down here?
Theta.
So I'm breaking up the triangle. I'm just gonna rewrite the triangle over here, and let's keep the same color coordination. I have weight acting down. I have that is the triangle I'm breaking up. I have two sides. Is this the adjacent or the opposite side to the angle?
Adjacent.
Which trig function is associated with adjacent?
Sine.
This is going to be the weight times the cosine of theta. And therefore this one is weight times the sine of theta. I am making the claim that my force diagram can be rewritten. Normal force acting this way. W sine theta acting down the ramp. W cosine theta acting towards the ramp. I'm making the claim that this force diagram and this force diagram are the same thing. Because if I add these two vectors together head to tail, I end up with weight. So all I'm doing is just, the equivalent would be, if I have 7 plus 5 and I'm trying to add them, I know 5 is 3 plus 2. And then it's 12. So all I've done is I take the larger thing and I broke it up into the smaller pieces. That's the scalar analog. And, all right, we've done the decomposition. Questions before we move on, before we do the next bit? How many equations of motion will there be?
2.
F equals ma as my starting point. What are the two equations of motion? Or what's one of them?
W, 10.
I have only one mass here, so I don't any subscripts. If you want a subscript, okay, then.
Cosine. Theta.
Right.
Minus y.
What's wrong with that? Pardon?
Would it be plus one?
And
Oh, yeah.
Is that-
yes, it would be plus y, and this would be negative. We said, when I established this, I established my coordinate system. That's the positive direction. Now, in this case, ultimately, it's not going to change our final answer, but we're trying to teach a method here. So whatever we establish here establishes positive and negative direction. That's in the positive, that's in the negative. So y minus equals what?
Mass times acceleration.
What's the acceleration in that direction?
0.
When you do the equations of motion, if one of the equations is not equal to 0, one where you actually have to solve for acceleration. I mean, there are problems I've given where, there's a problem that I've done on a number of tests where I gave you the force diagram and asked you to come up with the equations of motion. That's a situation right there where you might have different accelerations here, where one of them is not equal to 0. But for what we're trying to solve for the acceleration, you can pretty much be sure 99% of the time one of the equations is equal to 0. What's the other equation?
W sine. W sine equals mass times acceleration.
Equation. Done. Substitution. Well, yes, Keelan.
Can you kind of explain where everything from those equations came from?
All right, so it's the forces on the left-hand side, mass times acceleration on the right. So we have two equations because I have two different directions here. We're gonna have a J equation and an I equation. So I said J, the positive J was that way, was pointing up and to the right. So that's in the positive direction. That's in the negative direction. So I just did the ones in the positive direction minus the ones in the negative direction. So Y minus W cosine theta. Just for consistency, take that out. So it's just all the ones in the positive minus all the ones in the negative. And since there's no acceleration, that's why it's mass times 0. The other one, we said the acceleration was down the ramp. We said the acceleration was in that direction there. And so all the forces in the positive direction, there's only one, minus all the ones in the negative direction, there aren't any, is equal to mass times acceleration. Is that what you were looking for in the question? Any other questions before we do substitution? All right. For what do we have an independent formula? What, Martina, I think you just mouthed it. Yes, we have a formula for weight. What is the formula for weight? All right. So we have y minus mg cosine theta is equal to 0. And we have mg sine theta is equal to mass times acceleration. The first equation here is not going to affect us. We're going to add friction after this, and then this will matter, but we're not there yet. So from this one right here, since we're solving for acceleration, can we simplify it at all? Yes. I have mass in common. It is a factor in every term, so I can factor it out or cancel it out. And I'm left with a formula for acceleration is equal to g sine theta. Therefore, assuming this takes place on Earth, 9.8, some generic place on Earth, 9.8 times the sine of 57 degrees, which is 7.9 something, 96.
Meters per second.
What is it?
Meters per second.
Thank you. Together, we find crime. There we go. What is the actual number? Is it 7.96?
8.22.
Yeah.
Oh, I meant to do 53-degree angle. That's my issue. All right, 8.22 meters per second squared. There was a problem on the chapter 3 master set where you had a box going down the ramp, the 30-degree angle ramp. And I said the acceleration was 4.9 meters per second squared. That's because 9.8 times the sine of 30 degrees is 4.9. That's where that came from. In the original test, that was a test 1. It came from a test 1. The first part was for them to figure out what the acceleration was. But since I differentiated on the master sets, I didn't have to do that. Questions to hear? All right, because the excitement is building up so much here, we're gonna take a little break here, let you calm down a little bit. We're gonna add friction, add just a soupçon of reality, and then we will solve the problem again with friction. Yes.